Welcome to our cosmic journey. Today, we'll explore the incredible process of star formation and the vital roles stars play in the universe. Imagine the vast, cold emptiness of space, sprinkled with clouds of gas and dust. These are the stellar nurseries, the cradles of stars. Within these clouds, gravity ignites a chain of events, a cosmic ballet of collapse, heating, and ultimately, the birth of a star. Our story begins within these stellar nurseries, vast clouds of gas and dust adrift in the cosmos. These regions, often called molecular clouds or nebulae, are the birthplaces of stars. They float silently in the vast expanse of space, seemingly tranquil, but hiding a dynamic and chaotic process within. These clouds, composed mostly of hydrogen and helium, the lightest elements, are not uniform. They are peppered with regions of varying densities, like a cosmic patchwork quilt. Some areas are denser than others, and it is within these denser pockets that the magic of star formation begins. Within them, pockets of slightly higher density exist, regions where gravity begins to exert its pull. These denser regions act as the seeds of future stars. Gravity, the force that governs the motion of planets and the orbits of galaxies, starts to work its magic here on a much smaller scale. This gravitational attraction draws in nearby gas and dust, causing the dense region to become even denser. As gravity pulls more material into these regions, the pressure and temperature within them begin to rise. This process is the first step in the long journey from gas cloud to star. As more material falls inward, the cloud begins to collapse under its own gravity. This collapse is a critical phase in star formation. The once diffuse cloud starts to shrink, and its density increases dramatically. The gravitational energy is converted into heat, causing the core of the collapsing cloud to become hotter and hotter. This collapse is not a gentle process, it's a tumultuous event, a cosmic dance driven by gravity's invisible hand. The cloud's material swirls and churns, creating turbulence and shockwaves. These chaotic motions can fragment the cloud into smaller pieces, each of which can become a star in its own right. The cloud fragments breaking apart into smaller, denser clumps, each destined to become a star or a system of stars. These fragments, known as protostars, continue to collapse and heat up. Over time, nuclear fusion will ignite in their cores and they will shine as new stars in the galaxy. Imagine the sheer scale of this collapse, a slow-motion implosion spanning light years, a testament to the relentless power of gravity. This process, though slow on human timescales, is a fundamental part of the life cycle of the universe. It is through this dance of gravity that stars are born, bringing light and warmth to the cosmos. As the cloud collapses, it spins, a consequence of the conservation of angular momentum. This spin causes the cloud to flatten into a rotating disk, much like a spinning ball of dough flattens into a pizza crust. Within this disk, the process of fragmentation continues. The initial clumps break apart into even smaller clumps, each a seed from which a star or even a system of stars will grow. These fragments, now much denser than their surroundings, continue to draw in gas and dust from the surrounding disk. The process resembles a cosmic rain, with material raining down onto these growing clumps, increasing their mass and density. The fate of each fragment is now sealed. It is destined to become a star. Deep within the collapsing fragment, at its very core, the temperature and pressure begin to soar. This is a place where the laws of physics are pushed to their limits, where the very fabric of space and time seems to bend under the immense forces at play. The core, now a cauldron of unimaginable heat and pressure, is the birthplace of a new star. The relentless infall of gas and dust converts gravitational energy into thermal energy, heating the core to millions of degrees. This process is not instantaneous. It takes thousands, sometimes millions of years for the core to reach these extreme conditions. The gas and dust, once cold and dark, now glow with the heat of 1,000 suns illuminating the surrounding space. This hot, dense core is now a protostar, a star in its infancy. It is a delicate balance of forces, with gravity pulling inward and thermal pressure pushing outward. The protostar is a dynamic, ever-changing object, constantly adjusting to the influx of material and the increasing pressure and temperature within its core. The protostar is not yet a true star, not until it can ignite the fires of nuclear fusion in its core. This ignition is the defining moment in the life of a star, marking its transition from a protostar to a main sequence star. The core must reach a critical temperature and pressure for nuclear fusion to begin a process that can take millions of years, but it's well on its way. The protostar continues to gather material from its surroundings, growing in mass and increasing the pressure and temperature in its core. Each new addition of material brings it one step closer to the moment of ignition. Surrounding the protostar is a swirling disk of gas and dust, the remnants of the original cloud. This disk is not just a byproduct of the star formation process, it plays a crucial role in the growth and development of the protostar. The material in the disk is gradually pulled inward, feeding the protostar and helping it to grow. This disk, known as an accretion disk, continues to feed material onto the growing protostar. The accretion process is a complex interplay of forces, with gravity pulling material inward and centrifugal forces pushing it outward. The result is a delicate balance that allows the protostar to grow steadily over time. The protostar's intense gravity pulls material from the inner edge of the disk, adding to its growing mass. This process is not without its challenges. The infalling material can create shock waves and turbulence, which can disrupt the delicate balance of forces within the protostar. But through it all, the protostar continues to grow, inching ever closer to the moment when it will ignite and become a true star. As the protostar continues to accrete material, its core temperature and pressure continue to rise. Finally, a critical threshold is reached. The temperature at the core reaches a staggering 10 million degrees Kelvin, hot enough to initiate nuclear fusion. Hydrogen atoms, the most abundant element in the universe, are forced together under immense pressure. They overcome their natural repulsion and fuse, creating helium and releasing an incredible amount of energy. This energy, in the form of light and heat, radiates outward from the core, pushing against the inward pull of gravity. A delicate balance is struck. The outward pressure from fusion now counteracts the inward pull of gravity. The protostar has become a star. With nuclear fusion ignited in its core, a star begins its journey through the cosmos. This process, where hydrogen atoms fuse to form helium, releases an immense amount of energy, causing the star to shine brightly. The star enters a long, stable period of its life, known as the main sequence. This phase can last for millions to billions of years, depending on the star's mass. Our own Sun is a main sequence star, currently about halfway through its life. It has been shining for approximately 4.6 billion years and will continue to do so for another 5 billion years. During this time, the Sun provides the energy necessary for life on Earth, driving weather patterns and supporting ecosystems. During the main sequence phase, the star exists in the state of equilibrium. This balance is crucial for the star's stability. The outward pressure from nuclear fusion in the core precisely balances the inward pull of gravity. This delicate balance ensures that the star does not collapse under its own gravity or explode due to excessive pressure. The star shines brightly, radiating energy into space, a beacon of light in the vast darkness of the universe. This energy travels across space, reaching planets, moons, and other celestial bodies. Fueled by the ongoing fusion reactions in its core, the star remains a constant source of light and heat. These reactions convert hydrogen into helium, releasing energy that powers the star. The length of time a star spends on the main sequence depends on its mass. More massive stars have more fuel but burn through it at a much faster rate. Massive stars burn through their fuel quickly, living short, brilliant lives. They shine intensely, but for a relatively brief period, often only a few million years. Smaller stars, like our Sun, are more frugal with their fuel. They burn their hydrogen slowly, allowing them to shine steadily for billions of years. These smaller stars, while not as bright as their massive counterparts, provide a long-lasting source of light and energy. Their longevity makes them stable fixtures in the night sky. But for all stars, the main sequence is a time of stability, a period where they maintain a steady output of energy. This phase is marked by a consistent and reliable glow, a time when they shine brightly, illuminating the cosmos. This steady heartbeat of the universe is a testament to the enduring nature of stars, providing light and warmth across the vast expanse of space. And there you have it. From humble beginnings in molecular clouds to the shining stars that light up our night sky, stars are truly the engines of the universe. They are the cosmic furnaces where elements heavier than hydrogen and helium are forged, the building blocks of planets, and ultimately, life itself. The next time you gaze up at a star-filled sky, remember the incredible journey each star has taken, a journey driven by gravity, ignited by nuclear fire, and essential to the fabric of our cosmos. Stay tuned for more cosmic wonders.